today is actually going to be a really exciting lecture because we're finally going to create a currency. We're finally going to create a cryptocurrency. But before that, I just want to revisit one of the problems that we've seen before, which was this idea that we have two banks or a bank with two branches, let's say in Hong Kong and London. And we have a bunch of people who go to the Hong Kong branch and they deposit some money. And then the idea was that the Hong Kong branch should give them some sort of a proof that they have deposited the money. And they should be able to bring this proof to the London branch, and the London branch should be able to verify that this really came from the Hong Kong branch. And we saw a solution before. We're now going to see a much simpler solution using digital signatures. So the Hong Kong branch can just create a public key and a secret key. And I write it like this, a public key and a secret key. And now, of course, this can be using RSA or it can be using any other digital signature scheme. That's why I'm not using D and E here, because it's not necessarily RSA. As long as it's some sort of a public key signature, it's fine. And then the message that the Hong Kong branch is going to send to the London branch, remember we said that this message is going to be sent on an unsecured channel and everyone can see it and so on. We just say that the Hong Kong branch sends its public key to the London branch. Now we can assume that everyone else knows Hong Kong's public key as well. That doesn't really matter because the public key doesn't give them any important information. Now let's say that Alice goes to the Hong Kong branch and wants to deposit $100. So say Alice deposits $100. Here's what the Hong Kong branch is going to do. They're going to create a receipt. And this receipt is basically just a string that says Alice deposited $100. Okay, so I can take this whole thing and I can say this is the receipt. Okay, let me name, I don't know, let's call it R. This is my receipt. Now, what's the Hong Kong branch to do? They're going to just take the hash of this receipt and they're going to sign it. Of course, they can also add a receipt number just to make sure that the same receipt cannot be used twice. So let's say Alice deposits $100 and then we have some sort of a number appended to it. And this number is something that is chosen by the Hong Kong branch itself. So you can think of this as a serial number. It can be thought of as a nonce, whatever. So the Hong Kong branch adds a serial number. And let's say this is really long. And that's it. That's the receipt. Now the Hong Kong branch just takes the hash of this receipt and signs it. Okay. So compute hash of R and compute the signature using the secret key that only the Hong Kong branch has on the hash of R. Now, what is the proof that I'm going to give to Alice? I'm just going to give her R and this signature, right? So the proof P given to Alice is just going to be the hash of R, or actually R itself, and this signature. Let's call this signature something. Let's call it S. So I give R and S. Okay. Now you can see that if Alice goes to the London branch and she wants to get the money back, she can easily give this proof to them. They can take R, compute the hash, and then they have to verify that S is a valid signature of the Hong Kong branch on that particular R, on the hash of R. And of course, they can do that because everyone can verify signatures. And Alice cannot fake this because only the Hong Kong branch can sign. That was the whole point of a digital signature. And also, the other nice property here is that because I have this serial number, I'm sure that Alice can take her money only once. So the London branch just keeps track of all the serial numbers that are paid out. They would not pay for the same serial number more than once, right? Okay, so now I can have a lot of people depositing in Hong Kong and taking their money back in London. And if you look at the amount of data that I'm sending, this message that I'm sending is just a public key. So I'm sending a constant length message from Hong Kong to London. I'm just sending my public key, right? And then the proofs that people are taking, so this proof key, is also constant length because it's just this string which has constant length, and then there is a signature, also constant. So everything is all one now. We don't have those logarithmic proofs and so on. And also another improvement here is that I don't have to wait for everyone to deposit so that I create the proofs and then ask everyone to come and get their proofs at the end of the day as we had to do before. So now it's like as soon as they deposit, I give them a proof and it immediately works. They can use it whenever. Okay, so this is our final solution for the bank with 2 branches problem. And it's much better than using the Merkle tree and all of the things that we saw before, but you will see that there was actually a point in introducing you to the Merkle tree because we're going to use it again later for something else. Okay. Now, here's the thing. Imagine that instead of having just 2 branches, this bank has many branches. And let's say that I want to create a decentralized cryptocurrency. So let's just imagine that I have a network, people can join this network, and everyone is like a branch of this bank, right? Now, the thing is that if someone deposits money, this verification that the London branch is doing, it's something that anyone can do, right? Because it was just dependent on the public key, and the public key is given to everyone. So that's the idea that I want to use to create a decentralized cryptocurrency, but I'm going to start with a half centralized version, and then we'll make it more decentralized as it goes on. So this is what you probably know as central bank digital currencies. They've been in the news quite a lot recently, and we hate them in this course, okay? So I'm going to tell you how to create them, but they're like the opposite of what a blockchain should do. Okay, so what is a central bank digital currency? The idea is that I want to have a central bank who's all powerful in the sense that it gets to create new units of currency. So only the central bank can print new money, okay? And also I want my central bank to have some level of control over the transactions. So again, if you think of normal banking, if you have a transaction that is doing something illegal and they find out, they can stop the transaction, right? So that's what we want our central bank to be able to do. So the central bank would be able to censor some transactions. But at the same time, I want to give everyone else some sort of privacy. I want to make sure that when I, for example, make a transaction, no one can really verify who the recipient is, right? If I pay you money, it's none of anyone else's business that I'm paying you. So I want to have some sort of anonymity here. You'll see that we actually call it pseudonymity. But I also want to have a central bank. Now, later on in next sessions, we will get rid of the central bank. But for now, I have the central bank. Okay, so I have to answer a bunch of questions. My first question, and this is something that I brought up in the last session, is about identity. So how to identify accounts. Now, again, if you think about real world banking, you just go to a bank, you have to give them all of your real world identification, and then they will create an account for you, and your account is connected to your real world ID. It's connected to your name, right? But here we don't want that. We want the accounts to be completely separated from our real world identity. So instead, I just say everyone can create an account for themselves. Okay, how can we do this? Well, if I just say that an account is a key pair, it's a secret key and a public key. that would be enough, because everyone can create a secret key and public key on their own machine. And actually, it's very unlikely that two people create the same keys. There is a tiny probability that two people create the same keys and then they will share the accounts. But the probability is so low that we just assume it never happens. It's like 1/2 to the power of 256 or something. It's astronomical. So this is how I create accounts. I say that each user creates their own account. And an account is basically just a public key and a secret key. Okay. And of course, it's in the name. The secret key is secret. Only the user knows it. The public key is public. Okay. So when I want to send money to someone, I don't actually say I'm sending money to Alice. I say I send money to this public key. And what that means is that if someone wants to spend that money later on, they have to give you a signature that can be verified with that public key. So only people who have the secret key can spend the money. Okay. So basically, the identity that I'm using is the public key. This is the identity. If I want to send money, I don't say I send money to Alice. I say I send money to the person with this public key. Now, in the rest of the course, I'm still going to say Alice and Bob and so on, but just remember that it's not their actual names. It's just their public keys from now on. Whenever I say someone sends money to someone else, I just mean using their public key. Okay, that's the first question. The second question is something that I kind of answered. And it's, how do I make sure that no one can spend someone else's money? Okay. So this is what we call proof of consent. If some money is used, how do I make sure that the owner of the money actually consented to it? And again, this is just digital signatures, right? Okay. So the third question I have is how to create money in the first place. Because the previous ones tell you how you can transfer money. So if I have some money that belongs to a particular public key, I can create a transaction that sends this money to some other public key and I can sign it. And everyone else can verify these signatures. But now the question is, where did the money come from in the first place? So how is money created? And here I can just say that, well, this is the bad answer that I have. The central bank does it. Okay. So the idea is that the central bank has the ability to just give people money out of nowhere. Okay. And finally, our last question is, how do people know about the transactions? So how are transactions propagated? I'm going to write TX for transactions. And the answer here is that I'm going to have a peer-to-peer network. So I'm going to assume that there is a network of people, and this can be using the internet or whatever other means of communication. In the real world, of course, it's the internet. So let's say I have a network. And whenever someone hears about a transaction, they just tell all of their neighbors about it. And then the neighbors keep doing the same thing. So if you make a transaction at some point, you just tell your neighbors, they tell their neighbors, and so on. And at some point, everyone knows about all the transactions that have happened. Okay, so this is what we call a gossip protocol, because it's pretty much like gossip. Okay, so we kind of have an overview of what we want to create here. Let's actually create it. So I have to define what a transaction is. So I'm going to say what my transaction is like. Now, here's how I'm going to create a transaction. I'm going to say that every transaction has a bunch of fields. So it's just this thing. Now, it can have a recipient, right? So I say that it has a recipient. Actually, let me erase this. I say that it has a recipient. And by the way, I sometimes call the recipient an output. And of course, the recipient is always a public key. Okay. So this is just a public key. Of course, it's going to also have a sender. And this is also a public key. And we said that we need a signature, right? So I need a signature. And this should be a valid signature by the person who's sending it. Now, I can have this kind of transaction, but if my transaction has only these fields in it, the problem is that everyone in the network has to keep track of everyone else's balance, right? So I have to keep track of how much money this sender has so that I can see if they have enough money to send this money to the recipient. Oh, and of course, there is the amount. Most important thing that I forgot, right? Okay. So instead of this, I'm going to say that instead of saying this is the amount of money that I want to send from my account and having the concept of accounts, I want to say I only have transactions, and I'm going to point to a previous transaction in which I got this money. Okay, so I'm not going to have a sender. Instead, I'm going to have a bunch of previous transactions, and I'm going to call these inputs, in which I got this money. Okay, so these previous transactions, they're pointers to the previous transaction, and of course, pointers are hash pointers in this course. Okay, so this is what I'm going to have in my transaction. And by the way, whenever I have a signature, it's going to be a signature on the whole thing. So I'm going to take the hash of every other field and sign that. That's what I call a signature on this transaction. Okay. So let's see what happens. Let me give you a simple example. So this is my example. Let's say that Alice pays Bob 5 Bitcoins. Let's say I'm already calling it Bitcoin. It's not really Bitcoin at this point, but let's use that as a unit. So how does this work? Alice is going to create a transaction. And by the way, I'm going to use this notation for the transactions for the rest of this course. Here we have the inputs to the transaction. And these are pointers to the previous transactions in which Alice was paid. Okay, so maybe she wants to pay 5 Bitcoin. She has to say when she got these 5 Bitcoins. She has to give me some pointer to previous transactions. So these are the inputs. And these are just hash pointers to previous transactions in which Alice received maybe 1 Bitcoin here, 2 Bitcoin here, 2 Bitcoin here. Okay. She's going to have to create an output, and this output is just going to be Bob's public key, or just Bob, right? So it's saying that I'm paying Bob. It has to have an amount, so the amount is 5. And most importantly, you have to sign the whole thing. It has to have Alice's signature. So it's going to have a signature. I'm going to just write S here. Actually, the signature is public. So this is a signature by Alice, by Alice's secret key on the whole transaction. Okay, great. Now let's say that Bob wants to spend this money. So maybe Bob wants to send these 5 Bitcoins to, let's say, Carol. Now, he has to do something similar. He has to create a new transaction. And this new transaction is going to also have inputs and outputs. Now, in the input, Bob is just going to point to this previous transaction. So, and again, a pointer is just a hash. So he's just going to put the hash of the previous transaction. So it's telling everyone, hey, this is where I got paid. This is where I got the 5 Bitcoin. And then I have the amount, 5. I have the signature by Bob. And let's say this was a signature by Alice. And of course, in the output, it just says Carol. And this means Carol's public key. Okay. Now, here's the thing. If these transactions are just announced on the network, so like this, whenever I want to make a transaction, I just create the transaction and I tell all the neighbors in the network, everyone that I'm connected to, I say, hey, here's a transaction. And they just verify this transaction. And of course, everyone can verify a transaction, right? Because presumably they know all the previous transactions. So they can verify that this previous transaction existed. And they can verify that Bob was actually paid here. They have Bob's public key. Now, Bob is saying, I want to take these 5 Bitcoins that I was paid here and give it to Carol. So he's giving Carol's public key. They now know that it belongs to Carol. And of course, they can also verify that this is a valid signature. And if it's not a valid signature, they would just ignore the transaction. It's just spam if the signature doesn't go through. Right? So that's how we're going to make the transactions. We're just going to create the transaction, give it to the network, and then the gossip protocol takes care of everything. And after a while, hopefully after a few seconds, everyone on the network would know about this transaction. And so everyone on the network knows that the 5 Bitcoins belong to Alice. Right? We will see some problems with this very soon. Okay. But this is how my transaction is going to work. And I'm not going to really change this much. I'm just going to extend it a little bit. So here's the thing. Normally, we're used to transactions that have only one recipient, right? But I'm going to allow transactions with several recipients. It's just better. Like, I want to create a single transaction that sends different amounts to different people. I should be able to do that, right? Maybe I create one transaction in which I use 5 Bitcoins that I received before, and I pay 2 Bitcoins to someone and 3 Bitcoins to someone else. Why should I create 2 different transactions for that? I can just create one transaction, right? So this is what I can do. So I can have transactions with several inputs and outputs, basically. And this is a very simple extension of our concept of transaction that we had before. So again, I have a transaction. It's going to have several inputs, right? And each of these inputs is just a pointer to somewhere where I received some money, right? So maybe I received 1 Bitcoin here. I'm just putting a pointer to it. I received 2 Bitcoin here, and I received 1 Bitcoin here. Okay. And now I'm going to have a bunch of outputs. And maybe I want to send 2 Bitcoins to, let's say, Bob. And again, when I write Bob, I just mean Bob's public key. And maybe I want to send another 2 Bitcoins to Carol. And let's say this is a transaction by Alice. Okay. And then I also have the signature of Alice on this transaction. I mean, it's a trivial extension. You can say it. It's just that now my outputs don't just give me the address of the recipient, they also say how much, right? And of course, the obvious requirement here is that I shouldn't be able to create money out of thin air. I shouldn't be able to print new units of money. So whenever I'm making a transaction, everyone also checks that the sum of inputs is equal to the sum of outputs. Okay, so this is my additional requirement. On every transaction, I want to have the sum of inputs. Now I'm going to say greater than or equal to the sum of outputs. Okay. Now here's the thing. If I put 4 Bitcoins in, I shouldn't be able to take 5 Bitcoins out because that's creating new units of money, right? But if I want to burn some money, that should be allowed. It's my money. I want to burn it. Okay. So the sum of inputs doesn't have to always be exactly equal to the sum of outputs. I can create transactions that burn money. And we will later see that this is actually useful for some reason. Okay. So anyway, this is now our concept of transactions. And now we can talk about transaction validity, right? Because the idea was that whenever a transaction is created, it's going to go through this gossip protocol. So let's say I'm a node on this network. I'm going to receive a transaction. I have to decide, is this transaction valid? If it's valid, I should send it to all of my neighbors so that they know about it as well. If it's an invalid transaction, if it's spam, I should just ignore it because I don't want a lot of spam in my network, right? So how to verify transactions? So let's say you receive a transaction. What would you verify? Well, first of all, you verify that it has the right signature, right? So these inputs, they belong to someone, and whoever owns the inputs should have given the signature in this transaction. Okay, so that's the first thing that you do, verify signatures. And this is to make sure you have basically consent of people who are sending their money. Okay, what else should you check? You should, of course, check this additional requirement. You have to check that the transaction does not create new money. Okay. Verify that the sum of inputs is less than or equal to the sum of outputs. Then you have to also verify something else. You have to verify every input, right? Because these inputs are just pointers. So Alice is claiming that she has received 1 Bitcoin here, 2 Bitcoins here, 1 Bitcoin here. You need to verify that that was actually the case. So you need to keep track of all the transactions that have happened in the past so that you can actually follow these pointers and see if Alice was paid, right? So verify all inputs and make sure that basically they belong to Alice. And for this, as I said, you need the history of all transactions. You need all historical transactions to do this. By the way, this is also what's happening on Bitcoin. So every Bitcoin node knows all the transactions that have happened since 2008 when Bitcoin started. That's how they can verify that all the inputs actually belong to this person. Okay. Should I verify anything else? Okay. Yes. So the problem is that maybe Alice has spent some of these inputs before, right? Maybe someone paid Alice 1 Bitcoin and she's using that 1 Bitcoin as the input of her transaction to give it to someone else. But then maybe she's creating another transaction that is again using the same input, right? So I can have this kind of thing. I can have double spending. And double spending is this. I have some transaction that is paying 1 Bitcoin to Alice. right? And Alice is just creating new transactions. She's, let's say, creating 2 transactions. And in this one, she's paying 1 Bitcoin to Bob. And she's saying, my input is this, right? And maybe she's also creating another transaction in which she's paying the 1 Bitcoin to someone else, to Carol. And again, she's saying, my input is this. Right? So she had 1 coin, she's spending it twice. This is, of course, not allowed because she's creating new units of money. Right? So I have to make sure that my transaction does not do double spending. So what does this mean? This means that I don't only need to keep track of all the historical transactions, I also need to keep track of which outputs were already spent. So, because remember, the input to every transaction is an output of a previous transaction, right? I have to keep track of all the outputs, actually of all the outputs that are not spent. If I keep track of all the outputs that are spent, it doesn't really matter. Yeah. But anyway, for every output, I should know if it was spent before or not so that I don't allow them to spend it again. Okay. So, yeah. This is called the UTXO model, unspent transaction output, which basically means that for every transaction output, let's say I have a Boolean value that tells me, has this transaction output been used as an input of another transaction before or not? And when I'm verifying a transaction, I just make sure that all of the inputs were unused. Okay. But here's the thing. We have a problem, and our problem is double spending. And by the way, in this part of the course, this is the main problem that we're going to have for several sessions. So we saw what double spending means. It just means that someone is acting maliciously like this. So she has 1 Bitcoin, she is spending it twice. Now let's actually see what happens in the network if we do this. So let's say this is my network. And I'm just going to create something like this. Okay. And let's say that these 2 nodes, like the 2 extreme nodes, are really far away from each other. Okay. I don't know. Let's say this node is somewhere in China. This node is somewhere in the US. And they're not directly connected to each other. There are a lot of hops before they can get to each other. Okay. So here's what Alice is going to do. She's going to create these 2 transactions. Let's call this one transaction 1 and this one transaction 2. Okay. Now we know that at most one of these 2 transactions can go through. So if Alice announces transaction 1, eventually everyone in the network would know about transaction 1. And then if later Alice announces transaction 2, everyone would reject transaction 2 because they say this input was previously spent here, right? But here's what's going to happen. She's going to announce them at almost the same time. And let's say that she's using a VPN and she's announcing transaction 1 to this node and she's announcing transaction 2 to this node at the same time. Okay. Now, from this node's point of view, transaction 1 is valid because let's say that it satisfies all of these other requirements. And of course, it doesn't have any double spending because this node does not know about transaction 2 yet, right? So it says that transaction 1 is valid and it just sends transaction 1 to all of its neighbors. Okay, so these ones will know about transaction 1, transaction 1. At the same time, the same thing is happening on the other side of the board. This node in China hears about transaction 2. From their point of view, transaction 2 is valid because, again, they don't know about transaction 1. So they're just going to send this transaction to their neighbors. So this node is going to hear about transaction 2 first, and this one is also going to hear about transaction 2 first. So generally speaking, some of the nodes hear about the first transaction first, and then they think that the second transaction is invalid. And some of the nodes hear about the second transaction first, and they would think that the first transaction is invalid. So at some point, this node who has heard of transaction one sends transaction one over to this side. But this one has heard of transaction two first. So from its point of view, transaction one is invalid. It's just going to ignore transaction one and not send it anywhere else. On the other hand, of course, this one is going to send transaction two to this one, but the same thing is going to happen there. This node is going to ignore transaction two because it saw transaction one first. And now this is terrible. Why is it so terrible? Because the different nodes on our network do not agree on who owns what amount of money. So if you ask them who owns the 1 Bitcoin, this side of the network believes that Bob owns it, but this side believes that Carol owns it, right? So if Bob makes a transaction now that uses this 1 Bitcoin, this side of the network would accept that transaction because from their point of view, Bob owns that 1 Bitcoin. But this other side would reject it. And the same thing for Carol. And it gets worse. Like every transaction is going to double the number of disagreements that we have. And it's just going to get to a point where every node has a completely different view of who owns what. Okay. So what do we need? We need consensus. And by consensus, I mean that everyone on the network should reach an agreement on the history of transactions. Everyone should have the same view of what transactions have happened in the past. Okay? Everyone should agree on the history. Because if this happens, if everyone agrees on the history, then we're fine. Okay. How are we going to do this? We're just going to use our central bank. So our central bank is going to be our consensus maker. Okay. Central bank. So what is our central bank? Our central bank is just a node on the network, except that this node is special. It can do things that others cannot do. Okay. So here's what the central bank does. The central bank maintains a list of all the transactions that have happened until this point. Okay. So let's say maintains and publishes a list of historical transactions. And what is this list? This list is just a linked list. So we talked about this before in the case of a bank that you do not trust. Remember when your bank wanted to send you your account history, we said that every time it should send you a transaction that has a pointer to the previous transaction and also the bank's signature on it, right? So we're going to do that. So this is what's happening from the central bank's point of view. I'm going to have basically a chain of transactions, and we will soon see that we will create a blockchain. But let's say that this was the first valid transaction that the bank saw, this was the second valid transaction, the third, and so on. Okay. And let's say that there are n-1 transactions that the bank has seen, and the bank, again, it's just a node on the network, so it hears about the transactions in the same way that other people hear about transactions. And now the bank hears about another transaction, let's say one of these two transactions, and every time that the bank hears about the transaction, it also verifies them, right? So it does all of these checks, and if a transaction is invalid, it's just invalid. Otherwise, let's say that the bank hears about a new valid transaction. Again, this valid part is really important. And let's call this transaction. So the bank is just going to put this transaction N here, put a pointer to the previous transaction that he heard, transaction N minus 1, and it's going to sign the whole thing. Okay? And basically, we use the bank's signature as a verification that this transaction is finalized. This transaction is going to be there. So the bank, so let's say it creates, let's call this a verification. And I'm going to call it the verification over N. And what it's going to contain is transaction N. It's going to contain a pointer to transaction N minus 1. And it's going to contain the bank's signature. Okay. So the bank verifies that from my point of view, transaction N is valid. And then publishes this verification. Now, whenever I talk about publishing, I just mean using the gossip protocol. So the bank just sends this verification to whoever is connected to them on the network, and then they keep sending this verification over and over again. Okay? So what does this mean? Why does this give us consensus? Because now, let's say that the bank added the first transaction to their list, right? Half of the people here saw the second transaction first, but then they see the verification message from the bank that says that the first transaction is valid. So they will all update their situation to just match what the bank says. And that's how we get consensus, right? So very easy way to reach a consensus. Now, again, let's just go over this. So let's say that you are a node other than the bank. What should you save? You should save basically all the transactions that you have seen and also all the transactions that have been verified by the bank. Okay, so you keep a list of bank verified transactions. And you also keep a list of non-verified transactions. Okay. Every time you see a new transaction, which list should you use to verify whether that transaction is a valid transaction or not? Actually, you can use whichever you want. You can actually use the list of non-verified transactions. Why? Because let's say I'm here. Let's say I'm this node. I hear about transaction 1 first, and it's still not verified by the bank. And later on, I hear about transaction 2. Now, I see that these two transactions are spending the same coins. I would choose not to propagate transaction 2. Because even though transaction 1 is not yet verified, I know that someone is trying to do a double spending attack, and I'm not going to help them with it. So if I see that transaction 2 is coming here, and I've seen transaction 1 before, I would just not propagate transaction 2 to my neighbors. So I use this list, the list of non-verified transactions. This is used to check validity of new transactions. Okay. Now, but maybe, let's say this node was the bank, and let's say I'm this node. So I heard about transaction 1 first. And when I hear about transaction 2, let's say I have also this edge. Let's say I hear from someone else about transaction 2. I say, no, transaction 2 is invalid. I'm not going to propagate it. But later on, I see a verification from the bank that actually transaction 2 is the valid one. So when this happens, I would just update my set of transactions. I add transaction 2 to this set of bank verified transactions, and I remove transaction 1 from both lists because transaction 1 is now invalid. Okay. So the difference is that these transactions should come with the bank signature. And again, I know that only the bank can create those kinds of signatures. Right? Okay, nice. So now finally, I will have consensus, assuming that the bank does not cheat. Right? If I trust the bank, I'm sure that the bank will just create a valid list of transactions. And if the bank does not cheat, everyone on the network will eventually see the verifications from the bank, and everyone on the network will have the same list of transactions as the bank. Now, what happens if the bank wants to try to cheat? Can the bank, for example, put an invalid transaction in here? Well, no, because if the bank puts an invalid transaction in, it doesn't matter that the bank is verifying it, everyone else will reject it. Right? So every time that I'm hearing a transaction, I'm doing the verification anyway, and I'm not going to accept any transaction that is invalid, even if the bank verifies it. Right? So the bank's verification is only used for the consensus. It's not used for checking the other parts of the validity of a transaction. But here's what the bank can do. The bank can do something similar to this double spending. Right? The bank can create a fork. So let's say I have this transaction n-1, and ideally, the bank should only put one transaction after this, but maybe the bank creates 2 different transaction ends. And for both of them says that the previous transaction is transaction n-1. Okay, I have no defense against this, except to take the bank to the court and actually prove that this is the case. Right? So the thing is that the bank can cheat, but if the bank cheats, it's provable. If the bank creates 2 transaction ends here, I can prove it because I can just show the 2 transactions and say, look, these 2 have the same previous transaction. They have the same pointer to the previous transaction, and they're both signed by the bank. So the idea here is that everyone has some sort of anonymity. I don't know anyone's actual identity here because everyone is just using their public key that they created on their own machine. But the bank doesn't. The bank is a central bank that everyone knows about. So if the bank cheats, all you need to do is be able to prove that the bank has cheated. And that's assumed to be enough to deter the bank from cheating. So the bank does not cheat in this case. Okay. One more point. We said that the bank can create new units of money, right? How do I do that? Well, I just tell all of my nodes that when you're verifying that the transaction is valid, don't apply this one check, the check that says the sum of inputs should be less than or equal to the sum of outputs, to the transactions that are coming from the bank, right? So the bank can create transactions in which there is more money created, basically. So this does not apply to the bank. Okay. And actually, now we have another issue. And the issue is, what if the bank doesn't like me? And for some reason, the bank hears about my transactions, but it doesn't sign my transactions or put them in here, right? So I need to give the bank some incentive to actually do this. And we can do that using transaction fees. So the way I do this is, remember I said the inputs can be less than the outputs. If I put more money into a transaction than I take out, I would just say the rest of it is paid to the bank as a transaction. Okay. And this is my way of giving the bank an incentive to put my transaction into the list. Okay. So this is what a central bank cryptocurrency is, or digital currency. We will have a homework about this in which you have to figure out all sorts of security properties and what the bank can do and what it cannot do. But generally speaking, this is not a blockchain. And I don't care what the media says, it's never going to be the same as Bitcoin. So we don't like this. Again, one more time. And in the next sessions, we're going to see how to get rid of the bank. There's way too much power here. So again, imagine that I want to make a transaction and I'm even willing to pay the transaction fees, but for some reason, the bank just hates me. The bank can censor my transactions here. Because any transaction that doesn't get verified by the bank, any transaction that doesn't have the bank's signature would never be added to the list of bank verified transactions. So from the point of view of all the other nodes, I just don't have that transaction. Okay. Great. I'll see you tomorrow.